this business about representing parametric curves and other functions now with using vectors. So the one that we have investigated is the gravity force and the Newton's law of gravity. Okay, so that's the left top. And we made that step from functions of one variable to functions of two or three variables. So that r, which is the distance, it is a number, so it appears to be a function of one variable. That is how it is commonly stated. This one. Okay, but we make it just a little bit step off in a more look at it in a more advanced way if we want to actually do anything practical with it. And that is r is in fact the distance literally computed with the squares of the distance formula, and it instantly becomes function of three variables. Okay, so the graph is a roughly outlined graph on right. Okay, so it is well. Let me first show you the picture. There's a slightly prettier picture of. This one, this one. Okay, so that is the same graph done with the Excel. As you can see, so I had to cut off the top because it goes up so quickly, and well, the Excel doesn't do a very good job as far as texture is concerned, but it's not bad. The question that we may ask, and well, let's do it quickly, is the same questions as we did ask questions we asked about functions of one variable in calculus 1, and we are not doing at the moment any derivatives, so what we could ask about is the asymptotic behavior. Okay, so certainly it is easy to describe verbally what it means, but what do you see on this graph, either that graph or this graph? Asymptotic behavior.
Vertical asymptote at the origin.
Okay, so all right, vertical asymptote at the origin. What if we want to describe at the origin? What if we want to describe it as a limit? Remember, all asymptotes are essentially there are limits behind each of them. So, what does the limit look like? A vertical asymptote. So I could say, how about I say f being our force goes to plus infinity. Okay, so growing up as, and now this is a bit tricky. What is the what's happening to the independent variable? Say, forget about z. We have only x and y. So what's going on here?
Does it approach to 0?
Who exactly?
The function.
No, we were talking about the independent variables, which being x and y. So say maybe this is w or whatever. So that's the axis of the w going vertically, and the value is going up. But what is the dependent variable w is controlled by the independent variables x, y, z. So we have to put something as we have in the past, something that is referring to x and y.
X is the distance from the point to 0 approaches 0.
Yeah, pretty much exactly like that. So in fact, I'm going to use well, this is the easiest way to do it. So it is a function now of one variable, of not one variable, it's one of one vector variable. Okay, so now x, y, z now is you can still think of it as three variables. That what really it is a function of one variable which happens to be a vector. So it's x capital is a vector that is origin naturally at the origin, at the initial point, and the endpoints lie at the point x, y, z. Okay, so and then we're saying let the magnitude of that vector is going towards 0, so it's getting shorter and shorter and shorter. It doesn't matter which way. It doesn't have to be just shrinking like that. It could be rotating and shrinking. Okay, so and still it doesn't matter how you try to approach the origin. As you're approaching the origin on the xy plane, maybe spiral. It doesn't matter what's going to happen to the dependent variable. The height of the graph, it will go to infinity. Okay. So that's number one. There's number 2. What else? More asymptotic behavior.
F approaches 0 as
Okay.
the magnitude of x approaches infinity.
Okay, so as you can see, very similar. Once you, I'm sorry, that's supposed to be 0. As we adopt the vector approach, things are fairly complicated behaviors. Now can be written in a very compact way. So indeed, the f, the force, is approaching 0 as if you want to say, just in words, you say just we're getting farther and farther away from the origin of that planet. But really what we're saying is that either the distance, that's another way to look at it, to the origin from that point is going towards infinity, or the magnitude of that vector from the origin to the point x is approaching infinity. Okay, so we'll revisit all of this as we study functions of two variables, 2 and 3 variables. What else remains with this law is this is not a vector form of the law. It is like a function for a variable law or a vector valued function. But the output, remember, the output of the function of the force of the law is the force. Force is a vector too. So what I have here, f, is it appears to be a number, and it was plotted as the height. So it is definitely a number. But in reality, this one is a vector. And that part of the law, number 2 right here, has not been incorporated so far, right? So look at the graph. We only speaking of the magnitude of the vector, and we're saying nothing about the direction of that vector. Okay, so that it's not really that hard. So well, let me first restate it as follows. Now, once we realize it's a vector, this is how we would rather state it. It's the magnitude of that vector. The magnitude of that vector, and now we just have to be careful to point out the direction of the vector correctly. Okay, so we just need to rewrite. So this is about the magnitude of vector f. Okay, but now I just want to actually write the vector f. So this is no concern here. Positive, positive, positive. So I just write GMM. Okay, and then the force is dependent on x, which is the direction from the origin towards that other object. Okay, so once again, you can say x is a point, or you can say it is a vector that originates at the origin. So then the force will be then, well, not necessarily of the same magnitude, but like this. So force is pointing in the opposite direction. So if I put x here somewhere like this, I would have to have a negative sign. Okay, so that will give me the direction, right? This gives me the x is the direction towards the object, and negative x would be in the opposite direction. What remains is just to have the correct magnitude of the vector. Okay, so then 1 over x squared is not enough. How do I make the magnitude correct? Well, let me just write it out. This appears to be almost exactly as the original, as the magnitude form of our law, but you can see that does not quite work out. The direction is correct. The direction is correct, but the magnitude does not add up. If I take the magnitude of this vector, what am I going to get?
The product of the 3 constants?
No, I have a square here.
Oh,
So I will have 1 over, so I'm going to have this. Okay? So, which means that it's incorrect. So we have to adjust this formula in order to magnitude to work out correctly, and the answer is simply we put a 3 here instead of 2. Okay, so adding x here, I'm also adding the magnitude of x in the numerator. Okay, so to cancel that out, I need an extra magnitude of x in the denominator. Okay, so that will be the form of the Newton's law, the vector form of the Newton's law of gravity. Okay, so so once again, you can recognize the magnitude is here. You can see how it is still declining towards 0. You can see the direction is the opposite of x. And let me try to. Well, I have two versions of the visualization. This is one. Okay, so that is the arrows somehow have disappeared, but you can guess that they are directing towards the origin. And as you can see, it's getting shorter and shorter as we move away from it. Okay, and there's one more. This looks slightly different, and it takes some time to load. Let's hope it's going to work out. So okay, I'll give it a minute. In the meantime, okay, so that is the, what is the point? Let me just, why is it working? Oh. Okay, it's working. So, here it is. Okay, so it just takes time to refresh the whole thing, but you can see how the arrow is pointing towards the origin. Now, notice this is how we visualize functions of vector value. So if we go back to our equation, and let me add here just to make sure that we are on the right track. X is the point, the input. F is the vector output of it. So it means that to every point X, we can attach this vector F. Okay, and that creates a vector field. Almost literally, it's like every point has a vector attached to it. So once again, that's another topic in addition to this that's going to be discussed later in this course. So parametric curves, functions of several variables, vector fields. Okay, so that's roughly the plan for the rest of the course. And they certainly interact very aggressively with each other. Okay, so that's how it works. It's not a perfect visualization. It takes just so much time to load, but it mostly works. Okay. So the next topic in this bigger subject of geometry of multidimensional spaces is angles. Is the angles. The angle between vectors. So we don't want to think in terms of angles of triangles anymore. This is literally what we want to figure out. Say U and B, and we want to angle that. So we start with dimension 1. So vectors are numbers. And there are no triangles, it appears, but really we could still speak of angles, and there are still two possibilities, and that is if they're directed from the origin, they might be directed in the same direction or might be directed in the opposite direction. So if I pick the case of two numbers, well, let's say 2 and 3, I try to use vectors just to emphasize that point. 2 and 3, so the angle is 0. Okay, or they could go in the opposite direction. Say this is 2, and I go say -3. Okay, from the origin once again. Okay, so the angle is pi. Okay, so that's how we work our way. The idea is to work our way from the coordinates, and the numbers are coordinates. In dimension 1, there is one coordinate, so the number is that coordinate. Okay, so this is the 2 over here. So how do we figure out which one's which? And you can guess that it is true. Well, I want one more example, as a matter of fact. If I go in the opposite direction, -2 and -3, the angle is still 0. Okay, so it's easy to guess how we distinguish case 1 from case 2 algebraically. So case 1, same direction. How do we determine it algebraically? When what? X and Y. You see what's the relation? Both negative, both positive, right? So XY is positive. Case 2, opposite directions. It is when XY is less than 0. Okay? So that's how algebra kind of comes into play, and you can measure angles. That's the plan. This is the plan to measure angles. And so from that point, we proceed to make the following important observation, and that is that only directions matter. So the sizes of those numbers don't matter, and if I want to concentrate on that, then it is in fact entirely between 1 and 1. 1 and 1 in same direction, -1, -1 same direction, and 1 and -1 opposite. Okay, so the trick that we use to get get rid of the size and only concentrate on the direction is divide by its absolute value. Okay, so that we're gonna only care about the sign. So same sign, opposite sign. Signs. Okay, so I just divide x by the absolute value of x, assuming that xy not equal to 0, and then I have y divided by y. Okay, then indeed, when we divide by the absolute value, then these numbers are both have only two cases, plus or minus 1. Okay, so and then the cases to consider will be then, if I multiply, I end up with 1. So x over x times y over y. Two cases. So either it is equal to 1, then angle is 0, and equal to -1, then angle is pi. Okay, so and that is pretty much, well actually now the relation between these four numbers now is can be guessed. So correspondence between 1 and 0, -1 and pi. What is this? Can you see the function?
Cosine.
It is the cosine. Okay, so then the angle is cosine. I'm sorry, the cosine of the angle is that product. So the cosine of sine of the angle. So that's the conclusion that we just established between x and y not equal to 0 is this product. Okay? So that will be fully applicable to vectors now. We did this little analysis in dimension 1, but turns out it will be very much applicable if we just do it the right way. One thing is obvious, that if we proceed to dimension 2, is that absolute values will turn into magnitudes. Okay, so so once again, the idea is that direction is the only thing that matters. So direction of x, what is it? Is the direction of what we call the unit vector. The unit vector in the direction of x is x over magnitude of x. Okay, so if you had x here, origin x, and then you just x over absolute value of x, just shrinks it or stretches it, whatever the case might be, over absolute value of x. Okay? So the unit vector is simply a vector of length 1. Any vector of length 1 is called the unit vector. The unit vector in the direction of x is x over absolute value of the magnitude of x. So these are the terms we're going to consider, except the problem is we're not going to have, we have two coordinates. We have two coordinates. So it turns out that the formulas will be slightly different than from this. We will be multiplying component-wise. Okay, so it's called the dot product. X equal x1, x2, y equal y1, y2, and we'll multiply them component-wise and then add. X dot y is equal to x1, y1 plus x2, y2. y2. Oops. y2. Okay, so once again, I have comma here. Okay, and as you can see, we're sticking with going component by component like this. So one is multiplied, and then the other is multiplied, and finally they're added together. That's the dot product in dimension 2. Well, you can easily guess what's happening in dimension 3 for one reason why this is the way it is. If the dimension was 1, what we would end up with, if not simply multiplication of two numbers, which is what we just discussed. Okay, so that's the definition of the dot product in dimension 2. Then let's verify that things work out. The idea is, so is it still true that here's that expression, x dot y over magnitude of x, magnitude of y is the cosine of the angle between them. And the answer is yes. Let's verify it at least on a couple of simple examples. Say the two basis vectors. So this one is 1, 0. This one is 0, 1. What happens to the dot product? 0, 1 dot 1, 0 multiply component-wise. 0 times 1 plus 1 times 0 is equal to 0. And, cosine of pi over 2 is 0. So yes. Okay, cosine of pi over 2. This is my pi over 2. So 90 degrees will always give us, we are not getting the angle itself, we're getting cosine, which is almost as good, except for the problem that we might be facing is going to either clockwise, counterclockwise. So, the assumption is the second followed by the first followed by the second. So if the angle should matter, but the dot product does not tell which way it goes, it computes the angle between. So either this way or that way, rotation clockwise, counterclockwise produces the same result. Doesn't matter. So this is pi over 2, so that works out fine. It is indeed pi over 2 the angle. The simplest case. You can certainly pick a slightly more complicated situation. If I pick, say, how about I pick this one and that one? Okay, so once again, I want to confirm that we're going to end up with 0, and just the symmetry of the well, let's make it slightly more complicated. This is 45 degrees. Okay, so it is say 1, 1 times the first vector. The second vector is negative 1, 1, and once again I have 1 times negative 1 plus 1 times 1. It is 0. So once again, cosine pi over 2 is 0. So whenever, if and only if, as a matter of fact, if the angle is pi over 2, the cosine is 0, and if the angle is, if the cosine is 0, then it is either negative pi over 2 or pi over 2. Either way, you get 90 degrees. So they are perpendicular. One more example is, let's get, what if we have 45 degrees? So I have my, say 1, 1, and I'm comparing it to 1, 0. Okay, so then what I have here is I'm multiplying 1, 0 times 1, 1. I have 1 times 1 plus 0 times 1 is equal to 1. Okay. So, what's the conclusion? The dot product of these two vectors is equal to 1.
So if we divide 1 by the magnitude, we get 1 over square root.
Right, so first of all, we recognize that 1 is not the answer we are looking for, because cosine, when is cosine equal to 1? It is when the angle is 0. Okay, so angle is not 0. So that's why the point being that you have to normalize the word we use to consider, instead of every vector, consider instead a unit vector. Otherwise, the plan doesn't work. So instead of 1, 1, I have to, as the formula indicates, I have to divide by the magnitude. The first vector is 1, 0, so that's a unit vector. The second one is not a unit vector. Its length is, in fact, well, 1 and 1, and square root of 2. That actually is something that we're going to need anyway. To normalize, to turn the vector into a unit vector, we're going to need its magnitude, square root of 2. So the unit vector in that direction will be that thing divided by square root of 2. So this is 1 and this is square root of 2. So that is the complete formula. The dot product of the numerator and the just multiplication looks exactly the same, by the way, but what you're going to do. Multiplication of numbers in the denominator. Okay, so in that case, we are ending up with the numerator works out the same way as above, this one, so I still have 1, but this time it's divided by square root of 2, and either you recognize this as cosine or square root of 2 over 2 is a more familiar way to put it. Doesn't matter, this is cosine of pi over 4. Okay? So that works out just fine. So let me just state for completeness sakes so in R3, say x1, x2, x3 dot y1, y2, y3 is x1, y1 plus x2, y2 plus x3, y3. So component-wise multiplication, and that is your number. And it is less obvious than now that all the angles still apply. So this is a three-dimensional case. So the vector is expressed in terms of its three components, but the two vectors are still defining nothing but a plane. Even in R3, it is still happening. Everything can only possibly happen on the plane. Okay, so then the angles, everything's still applicable, even though certainly will need some proof. But before we do that, let's do in Rn. So I have a vector vector x dot vector y. So x is equal to x1 xn, y is equal to y1 yn. What is the formula then? We add n terms. So we rather better use appropriate notation, either dot 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 or the sum. So x1, y1, just we start the same way as before. Dot dot dot, xn, yn. Okay, so that works in any abstract space of any dimension, and it has this pretty much the same meaning. Remember well, we will review that in a minute, but as you remember, we had that situation when you have an abstract space, could be a space of prices, for example, and then the angles matter. Okay, so for example, remember the say investment advice, and you might want to express to see how closely you follow that advice. You want to split or decompose your vector into two vectors, into one of which is known to be the advice, and then you see how far this is the advice, and this is you looking at how far off you are. Okay, so that works out, and it makes just as much sense as in the physical space. Okay, so the angle matters. Okay, so the other way is with the sigma. So k from 1 to n. Xi, Yy, Yi. That's the definition. Okay, so the definition of the dot product. The number one observation is that the magnitude of a vector can be expressed in terms of its, let me make these capital. The magnitude of a vector can be expressed as I have made them capitalized. So the magnitude of vector x can be expressed in terms of a dot product, right? Look at it. The magnitude is the sum of the squares, square root. Okay, so here we're doing multiplication, except we're multiplying the coordinates of components of the vector by components of the other vector. So what if we make it the same vector? So it will be xi. So if xi is equal to yi, then we're going to get a bunch of squares, right? So, well, there you go. So it's a square root of x1 squared, xn squared, okay, and then we can write it this way: x1 x1, xn xn, square root, and that compare it back to our definition, and the answer is simply the dot product of the vector with itself, square root. Okay. So the dot product contains, that's now, if we summarize what we just have discovered, haven't proven, but at least we have discovered, that the dot product, the coordinates, the components of the vector, as well as its dot product gives us both all the angles and all the distances. So that's a pretty good way to do geometry in any space if we can measure distances, and we can also measure angles. Not measure, but rather evaluate. So knowing the components gives you enough information, so whenever necessary you can find the angle, and you can find any angle you can think of, as well as any distance. Okay, that's what you can expect from fully developed geometry. Okay, so that is a computationally fairly straightforward thing. I guess it's worth just mentioning that how different this operation is from what we have seen, and we already have some vector operations. Once again, we have vector addition. We're adding two vectors to each other. The result is another vector. Okay. Then we can multiply a vector by a scalar, which also produces another vector. So in other words, if we're doing these operations, we stay within the vectors. Okay, so like this. Okay, say These are vectors. So addition of 2 will still be, if you pick 2 vectors and they produce a new vector, that is also a vector. Okay? Either addition or scalar multiplication, they keep these operations within the realm of vectors. However, if I try to do scalar multiplication, the result will be a number, which is, well, it's not a vector. So this is dot product. So dot product produces numbers, and that is a very new kind of operation. However, it is we could try if we look hard. There are similarities with something fairly recent, and that is, what if I go back to dimension 1? Dimension 1, then this kind of multiplication over here, what is it? It is a function of 2 variables. Okay, so that's a function of 2 variables. X and Y are the 2 variables, and produces a number, and it varies between -1 and 1, right? So this kind of expression. And what else? And then it's what has changed is only that we have more variables. Okay, so the dot product is, in that sense, is really not a vector operation as much as it is like a function of many variables. A function of many variables over there is have 4 variables, right? X, Y, the 2 vectors, each of which has 2 coordinates components, and then so that makes a function of 4 variables. Okay. We move to dimension 3, we have 6 variables. Right there, look at them, those are the 6 variables. Not a very complicated function, and also, even though, like I said, it is entirely about components of vectors, but really there is a geometry behind it which is independent of the choice of Cartesian system. We change the Cartesian system, we change the components, but and that's a nice thing, is that the dot product does not. The dot product remains the same regardless of the Cartesian system, which otherwise the geometry wouldn't work. Remember, same with the magnitude, by the way. You don't want to change the coordinates, the component of your Cartesian system, and suddenly distances have changed too. Okay, or if you don't want to change the Cartesian system, and suddenly the angles are different over it. So because the Cartesian system is pretty much man-made, and the rest of we're studying something that might be actually independent of our experience, or certainly not from the tools that we use to study. So we look at the world and we add the Cartesian system to it in order to pre-measure everything that's what's going on, but that is artificial. Okay, so we should be able to still measure angles or distances with respect to a different Cartesian system, and the answer should be the same. Okay. So properties. Just like with Cartesians, with vector operations, or vector algebra, I don't want to call this vector algebra, even though it is which you take 2 vectors and put them together, but because the output is a number, that doesn't quite fit into what we have been doing. So properties. So every operation or combination of operations have properties, and that's no exception. So remember, we didn't have too many properties. Well, we actually have like 8 properties of vector algebra when the combination of scalar multiplication and vector addition. Now we are throwing in the 3rd operation, the dot product. So of the dot product. Okay, so x dot y. Well, one thing comes right to mind, I hope, is the commutativity. If you just look at the formula, it doesn't matter. So just like we have commutativity of numbers, so we can flip these 2 and those 2 and these 2, then we can flip the whole thing. So x times y, y times x is the same, and so once again, this is the angle. If we are talking about angle, it is not angle from x to y, it is angle between x and y, so it doesn't matter which way. So this way, measuring the angle, or we're measuring the angle that way, it is the same result. That is the unfortunate thing that we had, is actually an unfortunate thing, but that's what cosine gives us. So it only measures the angle one way. Now let me write out x1, y1 plus x2, y2 for dimension 2, just as an illustration of why this is true. Now I'm using commutativity of numbers to do this. Okay, and that is the same. These two are obviously the same, and so this is the left-hand side, this is the right-hand side of the property. Okay. Well, and then there is let's say associativity. So when you combine more than one operation, and does the order matter? It's actually associativity of scalar multiplication. Let's say cx. Okay, so we have vector x, we multiply it by c, which is a number, and then we could go with the dot product by y. Okay. Or we could instead do this. We multiply x and y dot product and then multiply by c, like this. And the answer is this. So there is a point here. That is why the formula for the cosine works. So what does c do to the vector? It stretches it. So that should not change the angle. Okay, so and indeed it does not, as you can see from this formula. The angle will be the same if we just divide by the magnitude. Okay, so anyway, let me demonstrate how it works. So this is how it is. So I'm looking at the first, what's in parentheses first, so it will be cx1 plus cx2, right? So my vector is x1, x2. I multiplied by c, and now I still have to carry out the dot product multiplication with y1, y2. Okay? Okay, let's carry it out. No, that's not right. What about that? So I still have two vectors. cx1, cx2, like this. Okay? So exactly, this is the cx vector. So each component of x is multiplied by c. We have our new vector, and then the second vector is still the same. Okay, so now if we carry out the multiplication, what do we get? We have cx1 multiplied by y1 and cx2 multiplied by y2 added together. That's the dot product. Okay, so if I compute it, and now I can just factor c out. cx1 y1 plus y1 x2 y2. Okay, and that is this. So this is how it works. Okay, so you can easily imagine what happens if you have more than two components. Works out the same way, except you just insert dot there, and that works out exactly the same way. And as I said, the meaning of the geometry is the stretching does not change the angle. Okay, so here the interchanging x and y does not change the angle between them. Okay, that's the geometric meaning of commutativity. The geometric meaning of associativity, that stretching of the vector or of the. In fact, there is a third version here. I could write it this way: x dot cy. It will be the same result. So on the left, I'm stretching x and looking for the angle with y, or I stretch y and looking for the angle with x. The result is the same. The angle is the same. You just stretch it. The next one is slightly more complicated. Is the distributive property. So now we are bringing in finally vector addition. So scale multiplications first. The dot product by itself. Okay, now dot product versus scale multiplication. Now dot product versus vector addition. So well, x times y. Say x times y plus z on one hand, and x dot product y plus x dot product z. That is distributive property, just the way we know it applies to numbers. And what do you know? That's exactly how we prove it. It is what you can do with numbers. If you write these things in a more vertical way, then that certainly is helping. Now let me try to do it this time. So remember, there is the alternative notation for vectors is as columns rather than the rows. So those are rows. Well, let me do columns for a change. So I have x, x1, x2, that's x. I multiply dot product by y1, y2, plus z1, z2. Okay, so now let me carry it out. Okay, so I'll keep x, and I just carry out the addition, vector addition, component-wise. So I'll have y1 plus z1 plus z1, y2 plus z2. So that is my new vector, the one that was in parentheses. And now I am carrying out the dot product here. Let me put the dot product here. Okay, so what do I have? Remember, I multiplied component-wise. So I multiplied first by first, second by second, then add them together. So it will be x1, y1 plus z1, plus x2, y2 plus z2. Okay, so at this point, everything is in fact about numbers now. And if we just go back and look at the name of the property, it's about distributive property, and we have two places for distribution. So at this point, we can forget about the vectors and just look at the distributive property of numbers. And these are numbers, and we just distribute them. We distribute multiplication over addition, and well, naturally, we have what we expect. It will be x1, y1, plus x1, z1, plus x2, y2, plus x2, z2. Okay, so we have distributed it, and now the point is to just, we got to work our way here, and we do by simply what we are reassembling. We have to combine these terms appropriately, and if you look at it carefully, we have to combine y's and x and z's separately. So let me circle. So we have to combine these. These contains y's, and these contain z's. Okay, and I recognize these. What these? So what is this? Combined together.
It's x dot y.
It is xy. That's right. X. This is xy. This x dot y. So. Okay. And what is in the yellow is what's left. It's x plus x dot z. I mean, if you know ahead of time that it's supposed to work out, well, it will work out. You'll just see that you're getting closer and closer to the correct conclusion. So more and more operations start to pile up, and certainly that's not going to make things easier. Just some practice with these kind of properties would help a lot. Okay, so I'll see you tomorrow.